everybody was able to access the recording and audio if you needed it last week. I know there was a few people who emailed me that they had missed the course. So the way I uploaded that to the eConestoga, does that work for everyone? Does it not work for some people? I guess that's more important. Open up my chat. Okay. So Olu, it does work for you or it does not work for you?
It worked for me.
Perfect. Okay. So I'm going to plan to do the same thing. Do people want just the video or do you want the audio? Does anybody have preferences? It's a lot of data that's sent up if nobody's ever going to listen to the audio. Video is better. Okay. Okay, unless somebody says otherwise, I'll just upload the video today. Okay, so now that I'm finally sharing my presentation, so we're gonna go over the 4 main programming languages you're gonna find in most of your industrial controllers. Scan order of those languages, examine on versus examine off bits, what is a bit, what is a byte, how do these relate to control logics data types, what are data types. We're going to do some converting to binary to decimal, decimal to binary. So again, the primary programming language, at least for Allen Bradley's, that I see everywhere, a lot of people have standardized to this, is ladder logic. It was designed, it's a graphical programming language that is designed to look a lot like relay logic. So if you have experience looking at electrical drawings, a lot of the basic stuff in ladder logic will be familiar to you. Next, we have structured text. This is closer to some of the text-based programming languages, although, again, not as sophisticated as some. You don't have fancy repositories. You are limited to what is available in the controller. The next one is another graphical interface. It's called function block diagram. It's a little different. It kind of flows from left to right. All of these function blocks are, if you're familiar with programming and some other languages, the function blocks are little programs in themselves that have input and then output pins. So you can kind of see the lines that the program kind of flows through from function to function with inputs and outputs. And then the last very common one here is called sequential function charts. Similar to function block diagrams. I haven't used it too much, but it is a nice program for language for very repetitive sequences. We'll get to that in a few minutes. Okay. All right, so why did that freeze? So ladder logic, the order of execution, scan order starts from the top left. The PLC scans the logic in a particular order, left to right, and then top to bottom. So this is a screen grab from a generic ladder logic program. So again, you see with the ladder logic, you're going to have your rungs labeled down the left-hand side here. So we're going to execute code left to right. So through the first bit, which is an examine if closed, into an output, which is an operation. Then it's going to move down to the next rung, scan across, move down to the next rung. You'll see here that this branch, so they call these branches. If you were familiar with Boolean logic, this would be an or statement. So if this or this are true, so then what will happen is it'll scan to the start of the branch. It'll evaluate the first bit in that branch. Then it will evaluate the next branch down. If either one of them are true, then it will continue on to the end of the branch or that ladder. And then it'll skip down and continue. Oh, there's more. No, that was it. So you can see discrete input instructions can be placed in series or in parallel. So this is the series would be and. So if for this example, if 030 and I61 2, then execute the output. For rung 2, you have here if I61 0 or 032, then this would then be an and. We would then execute that. Are there any questions so far? No. So discrete inputs can be used with examine if on or examine if off. So again, those familiar with looking at relay logic, you have your normally open and normally closed contacts for your relays. So the example is if an examine if on, it would be if you have a switch, a proximity switch, if that proximity switch is not activated for this 032, then it is not true, and therefore this rung will stop executing at this bit. The other one with the slash through it is an examine if off. So if there's a proximity switch that is not activated, or another example would be if you have a pump, if you want something to happen only if the pump is off, you don't necessarily want to try to start a pump. We're looking at, well, if for this example, if this rung is true, but if a pump were not running, then you could start. Does that make sense? It's a little, this is where the Boolean logic kind of catches some people. And when we get into programming, it'll become pretty clear. The last bit you see here are these output energizers, so OTEs. These are like your coils for a relay. So when this rung becomes true, so whenever for rung 0 here, if I61 0, if this became true, this is tied to an actual digital input. If it became true, then this local 03 data point would activate. If 030 here were activated, all of these examine if on bits would then turn green. So you can see here where these bits are green, that means that these inputs, these bits are on, or if their binary equivalent is a 1 versus their binary equivalent of this one is a 0. Obviously, there are more programming bits that you can use here. We're just quickly covering that. Analog inputs can also be used in ladder logic. So this is an example of a greater than instruction. So if source A, which right now is channel 0, is greater than source B, which is 0.8, then this would then become true. This OTE would be turned on or written high, depending on how you want to say it. This is an example of a less than or equals to. So LEQ, if this said LES, then it would just be less than. Again, source A, channel 0 is less than or equal to 0.4, then 035 would become true. This is a compute instruction, very common instruction that just does math. So there's some funny syntax that you have to use when you're using these. F1, the help menu, very, very useful inside these programming languages. Every PLC does a lot of the same thing, and they all do it just a little differently. This particular rung here, when I610 is on, then it's going to compute. So this scaled value is equal to 0.2 plus channel 0's value times 1.5, which is 0. I don't think this is executing code, which is why it's 0. Again, and more, lots you can do. Structured text is executed the same way. So top to bottom, left to right, like reading, like every other text-based language I've used. So the first rung, while pump is running and not pump faulted, do fill tank equal 1. So fill tank would be a tag, write fill tank as 1, exit, and while. So examples for structured text would be for equations, repetitive logic, process control. Again, a lot of end users, you won't find a lot of structured text in the main body of some code. You'll find custom functions written in them. I have come across some PLCs that have been programmed all in structured text, and they are a nightmare to troubleshoot. So if you do become a systems integrator, you do start working for an engineering firm, you're going to find that a lot of end users will have their own standards. Typically, they'll have even base shell programs, and you'll typically follow their standards. Ladder logic, again, is, at least for Allen Bradley, is by far the most common. Function block diagram. So the order of execution is defined on how the elements are wired together. So if you, this one is organized fairly well. So we're starting from on the left here. This is an input. So you're going to start from your inputs and roughly how they land on the grid when you put them into the program. It's less like ladders, and there's a if you imagine a grid, not unlike a chessboard, where the top left is roughly where you're going to start. But if you don't have an input in the top left, it's going to find the first one. So kind of how the elements appear on the grid is how they're going to execute. So for this example, we're starting with the input. So this flag would be associated with a particular tag. If that tag is true, this wire indicates that that is going into the input pin of this first function. This first function will execute some code, whether it's a timer, a greater than or equal to, a custom function. The output pin is then going to be wired into this function. This looks like an example of an AND. So, or an OR. So we have a input. If this input is greater than a value, here, if this and that are true, then we're going to output to this output flag. You can tell these are outputs just based on their orientation that kind of points like an arrow into the wire. Again, you can do almost anything you want in function block. There are some controllers that their primary programming language that they've been designed for is function block diagram. It's a very good graphical process flow looking software. And if you are very familiar with Boolean logic, looking at some of the gates, and gates, or gates, it's kind of designed to look a lot like those type of drawings. Are there any questions so far? And if I'm going too fast, please let me know. Okay. So the last main programming language here is called sequential function chart. The order of operation for this is top to bottom. These look a lot like, I can't think of flowcharts. So if you've ever seen a flowchart for like an SOP, where like, it's like, have you done step one? Yes. Was it true or false? Yes. You move on to the different steps. That is how these programs kind of flow through. So here we have execute the top task once, and then you're looking at the transition state beneath it. If the transition state is true, we're going to move on. Okay, so if it's not true, sorry, then we're going to go back up to the first step, execute and scan this step. If the transition state is true, then we're going to move on to step one, execute this logic once, and then check the transition states. You have two transition states down here. So when one of these conditions is true, we're going to move on to one of those steps. So if this transition, so if transition one is not true, we're going to look, is transition two not true? If neither are true, we're going to go back up to step one, and then we'll check the transition states again. If transition state one is true, move on to step three, execute this logic. If this final transition state is not true, we're going to come back up and repeat this step. And if it is true, we're going to jump all the way back up to the top. Does that make sense? So a typical use is to execute specific routines in a specific order determined by the PLC programmer. For these are great for very repetitive processes, whether this is a PLC programmer or the process engineer. Examples for something that looks like this, it could be as simple as a sorting machine where step one is conveyor runs. It's looking for a transition for a proximity switch. Is the proximity switch detecting that something's there? Yes. Step two could be activate an arm or activate a scanner to try to scan for a barcode, or it could even be activate a weight scale. And these transitions could be as simple as, is it above a certain value? If no, we might come back, we might kick it out to a machine to the left, or kick it out to a waste bin. Have we confirmed that the part's been clear? Yes, move back up to the top. Something that's super repetitive. These are great for, because you can visually see what's going on. Can FSC be used to reset a failed piece of equipment? Okay, so I'm reading a question here from Olu. Yes, but not great for that. So one of the pitfalls, and one of the reasons I don't see a lot of this, especially in the water and wastewater industry. I most of the time I saw this was in machines that don't really have a lot of fault states. If you had a machine that may jam, what you're going to probably do is program a jam function elsewhere in your controller that will stop this from running. So you're going to stop your conveyors, you're going to stop everything else in a different part of your program. And this will be like if all the permissives, if all the light curtains are clear, if all the switches are good, the operators holding their and on station, we're gonna run logic. So you're gonna program outside of this, and this is just gonna run your conveyor logic or run your very specific thing. If you have a whole bunch of fault cases, say you've got a process with 50 different sensors. So and forgive me, I'm going to use a lot of examples from water and wastewater. That's just where a lot of my experience comes from. But if you're running a water plant and you're looking at pH and temperature and chlorine, and there's 5 different ways that they can fail, and you've got 3 different types of pumps with VFDs, it's kind of tricky to program all of that in your SFC. So SFC isn't necessarily a great programming language for a system that might have to start up or might have to kind of stutter step to start up and do a bunch of different checks. I think the rest of this slide goes into, I think it's, for an example, this would be for like an HVAC system where everything's going to be exactly the same and there's going to be very small fail cases. Sorry, I'm very bad at long story short. I'm going to ramble on. Did I answer your question?
Yes, thank you.
I'm just waiting for a response back.
Yeah, thanks.
Oh, my speaker turned off. I'm sorry,
Yeah.
guys.
Thank you. Yeah.
Sorry, my speaker is on again. All right. So one example for the usage of this is an HVAC system. So step 1 is action is ready, waiting, no action to be done. So the transition state would be the room is above a certain temperature. The action is then start the cooling coil. Transition are the cooling coil is the contactor pulled in. Step 3 would be start pump to push coolant into the system. Then wait 5 minutes, then start fan, and then final transition is the room is below a certain temperature, return to start. So SFC programming can be used again for any repeated sequences. Another example is washing machines that go through the identical cycle every time. So if you have something that's very, very repeated, vibratory bowl feeders, if you need to do anything fancy at the output of those, this is a great language for something that is very repetitive. Again, we're gonna, like, with the programming languages, and there's other ones too. If you want to read more than you're probably interested in, IEEE has a standard that goes into detail what and how all of these languages should be laid out. I think it's 1631-A. I've skimmed through it. I don't recommend reading it, but if you want to, by all means. These are just 4 of the ones that you're typically going to find. If step 4 fails, does it go back to step 1? We don't have a step 4. So we got a step 3. So step 3 for this example here is it's going to do something and wait for this transition. If this transition doesn't happen, it's just going to hang up. So if something fails in here, so let's say inside step 4, it started this fan, well, you're going to have another routine outside of this. It's going to be looking at the fan. And if there's a fault for the fan, or this step in here could be a custom function that is called fan controller, you would have to kind of encapsulate the fault inside of that function block. So if whenever you start the fan up, it pulls in one coil and does some diagnostics, and if it faults, pushes out, you're going to then write somewhere else in your program that's going to stop and fault this entire, like I would guess that this, for this example, would be called the cooling stage. So, and then when somebody puts the HVAC system into a heating stage, like this code would never execute. And then the next piece of logic is going to look very similar, but the transition might be a greater than, or the temperature is less than, and then we're going to start a different pump and a different heat exchanger. If transition 1 is true and transition 2 is false, we'll wait for the if transition, so if we're in step 0 and transition 1, no, sorry, that's transition 0. If transition 1 is true, so they will, if transition 1 is 2, step 3 will execute. If transition 2 is false, then step 2 won't execute. No, so these will run, these will kind of flow in parallel. So one of the things with SFC is, as you can see, these parallel trains could execute differently. Now, it all depends on what the transitions are. So let's say for this example, transition, this is a temp, this would be your high temp. This was going to start your coil, and your transition down here could be your coils pulled in, and this transition could be wait 5 minutes, or it could be a coolant pressure. So if your coil is pulled in down here, we'd be waiting for the temperature of the room to come back down. This could be something else. So if this is coolant pressure and the coolant pressure is low, and this just starts the coolant pump, then it'll run. And as soon as the temperature gets low, all of your coils are going to drop. So once this transition's done, we're going to stop even looking in this code. So this is kind of the be all and end all. So if this is completed before, like if this, let me turn on my drawing. So if we come down here and this path completes before this becomes true, it's going to jump up here, and then we're just going to reset. So once the temperature comes back down, we're going to sit up here and we're just going to wait, and everything will be clear. So once we pass here, we don't go, we're waiting in this state for one of these to happen. And once we go through, we're going to jump back up. If this never comes true, we're just going to ignore it until the next time we enter the state. Does that help, Hardik?
Yes, it does. I thought step 2 and step 3 were independent of each other, but or more like transition 3 would look for that step 3 and step 2 were completed, hence it will proceed forward.
Yeah, so if you wanted to do that, then you would actually stack it differently. So you would go like this, you wouldn't have that one, and you would then come up. So you want to first SFC
series.
Yeah, series. You would do everything in a very specific order.
Oh, I see. This is like an or condition. Okay.
Yeah. So this is exactly that. So if this were a welding line or something, and this is a parts come in and it moves in and it moves down and hits a proximity sensor, and this robot runs, and then this transition could start a different robot, and you could have 10 or 15 of these. Again, I am really speculating on what this code is put for. Like nobody, like it's just an example of how it's executing. There's so many things that this could be doing. And again, there is no right language to use unless your end user says you must use ladder logic. If you're programming, if you've got a custom machine, and you have all 4 of these languages at your disposal, use the one that's going to be the easiest to troubleshoot. If you're doing very, very simple math, use structured text because it's super fast to execute. And why have 10 or 15 rungs of logic to move some data around? Whatever is the most efficient for a particular use, use it. Any questions on these programming languages before we go on to binary decimal? Has anybody programmed in any of these? I know like people who have done work on PLCs. Is it primarily ladder logic you've seen?
Yeah, mostly ladder logic and function block.
Yeah, again, that's the two I've seen the most of. Okay. So binary and decimal. So computer data in its simplest form is either 1 or 0 binary. To store the ones and zeros, we locate them in physical areas in the memory and we index that area of memory. The way the processor knows the value of address, I'm not reading that, of that address is 1, and that memory address is being used by a Boolean variable tag motor run. Does that make sense? So there's a lot in there. So that ABX, they're calling an address. So that could be a tag. That Boolean tag could be 1 or 0. So again, on or off. So we refer to the simplest form of data as a bit, which is a portmanteau of binary digit, a logical state that has one of 2 possible values. You may have heard of a qubit, which is a quantum bit. Wow. And the logical state has 3 possible values: 1, 0, 1, or the superposition of 0 and 1. I'm sorry, I didn't write that, and I don't know what that means. I think Quentin wrote a joke, and I should have taken that out. I don't find it funny. I'm sorry, guys. Ignoring the qubit part, does the binary bit make sense to everyone? It's really just either on or off, and then binaries, bits, and booleans, those are all used interchangeably in PLCs. So in a control logics, the bit is stored as a bool data type. Bytes. So a byte is 8 bits. So 4 zeros and 4 ones, that is a byte. So 8 digits shown above is a 1 byte. In 1 byte, any of the 8 digits can be 0 or 1. So the PLC data types that we see can be 1 byte, 2 byte, or 4 bytes. So however many bytes that the application demands. So I think, was it Scott, you were saying you used the PLC 500s and the micrologics?
Yeah, yeah, that's right.
So some of the older controllers, they will actually only use a 2-byte system or an integer data type. That's going to be a limitation of the processor inside of that particular PLC. When we get into the control logics, compact logics, I think Siemens will use double integers just because they have more powerful processors. They can use the larger data types. So An example of an integer is 2 bytes or 16 bits. So 16 bits or 2 bytes, if they're all 0. And then if we were to convert the integer above into a decimal, its value would be 0. And I apologize if this seems very basic. I just we got to make sure you get this before we move on. So are there any questions about that? No. All right. So some examples of converting binary to decimal. So some terminology here is that the rightmost bit is the least significant digit. So binary is a base 2 numbering system. So the left most significant bit in this integer would hold a value of 2 to the power of 15, where the rightmost bit holds a value of 2 to the power of 0, which is 1. So when converting the value of that integer into a decimal, we are looking at adding the ones together. So for that example, the 2 most right bits are 1. So we're adding 2 to the power of 0 plus 2 to the power of 1, which is 2, which when added is 3. And I'm sorry, this might be very basic to some of you. So again, more converting binary to decimal, rightmost bit, leftmost bit, we add the ones together. So 2 to the 0th position plus 2 to the 3rd, 1, 2, 3. We're looking at 9. So one more time before so we're looking at 2 to the 0, 1, 2, 3, 4, 13. I don't know why that skipped. 14, 15. So 15 is special in the event of a signed and an unsigned integer. So that means whether it's an unsigned integer, no negative numbers, or a signed integer, it could be negative. Does that make sense? So for that example, we're adding the 4th, 5th, 6th, 7th, 9th, 11th, and 13th bit together. So this value is 10,992. Any questions before I show you how to cheat and never have to do this by hand? So assuming all of you have Windows computers, if you launch your calculator, some of you will have a button on your keyboard that'll launch the calculator, and then click on that icon in graphical interface. That is a hamburger icon. That's the only thing you learned today. I'm sorry. You can then change that from scientific to programming. And what's going to show up here is you're going to see hex. Actually, if I do this, can you see my calculator, or do you only see my presentation?
I see the calculator.
So you've got a bunch of different options with this programming calculator. You've got currency converters too. Really powerful. I use this all the time. So when you plug in, you select which unit, I guess, that you're wanting to use, and you type in a value, and it will automatically convert into octal, decimal, and hex. So if you're on your computer, by all means, try it out right now with some of these examples. If you're on your phone, whatever phone you have might also have this. If you have a Mac and it doesn't, is anybody here using a Mac? No.
I am right now, my personal.
Yeah.
Yeah.
There might, they might have something similar. I don't use a Mac. When we do, pardon?
They do have one.
Okay. Don't do this. Like, understand the theory behind it, because it will help once you get into programming. And I'm going to show you, there's not very many examples of what you're going to gain from this in these slideshows, but I'm going to launch some PLC software and kind of show you why this matters. It seems pretty basic, but it's really helpful to be able to convert this stuff on the fly. So again, try it out on your calculators as we're going. So assigned integer data type, abbreviated to int in the control logics platform. An integer data types consists of one signed and unsigned bit. So the most significant bit, again, that's the one all the way to the left, allows the integer to store negative and positive data points. So that means that the 15th bit, if only that bit were true, the integer value is negative 32,768. The least significant bit is 0. There is a unsigned version of an integer where the 15th bit is no longer signed. Therefore, the most significant bit of an unsigned integer is 32,768. So this allows the unsigned integer to store values from 0 to 65,535, although it can't go negative. Does that make sense? So the range is similar. It's just on an integer, you're going to negative 32,768 to positive 32,767. But with an unsigned integer, you're able to go from 0 all the way to 65,535. Again, if you're using SLICs, these are important numbers to know, because if you try to write values higher than these into integers, you can fault your controllers. So this may seem basic. It's important to understand these limits. The important limits are going to be your timers and counter presets. They will not math overflow. So the newer controller logics and compact logics, the processors have some catches in them that will automatically prevent the processor from faulting. Also, excuse me, they use double integers, which we're going to get into very soon, and their limits are much higher. So if an int had a binary value of 1 with a whole bunch of zeros, without looking at a calculator, what is its value? Anybody? That's correct. It's negative 32,768. Thank you. If a uint had that value, it's 32,768. Oh, he's very excited about that. So if an integer had a binary value of 1, 7 zeros, then 7 zeros and a 1, what would its decimal value be? Negative 32,767. Because it's signed, this is 32,768 plus 1. And then if a uint had it, it would be 32,769. So this is a really fun one. I learned this one first. All ones in a integer is negative 32,768. And then adding all the bits together, you get -1. So if you ever need to write all the bits in an integer to a 1, you can enter in -1 as a decimal, and all the bits will write to 1. So you don't have to go through individually and hit 1, enter, move to the next bit, 1, enter, move to the next bit. Does that make sense? Anybody know my pain of having to enter in hundreds of ones to turn on a bunch of enables? No. So double integers. So these in 64-bit processors, and even 32-bit processors, I think, can run double integers. How many bytes is in a double integer? 4 bytes. It's just twice as big. Man, Quentin is very happy about this. So like I was saying with the double integers, your limit changes. What's that? 2,147,483,647. You're much less likely to run into limits when you're dealing in the billions. So data types, in a nutshell, a bit is either 0 or a 1. In control logics, a bool is 0 or a 1, and it's a single bit of information, but depending on how it's used, it might take up a byte of memory space. This is a little tricky because of the way it could be looked at inside the controller. If you're looking at a bool, an individual bit, if it's part of a full integer, it will take up the whole integer worth of memory on your controller. Byte is made up of 8 bits. So if you want a single byte in a control logics, you're looking for a single integer, a cint. 2 bytes is an integer, an int. 4 bytes is a dint. There's a handy chart. Any questions? No. Perfect.
In the program, does it tell you if it's a unsigned integer or a signed integer? Like, how would we know?
As the programmer, you will tell it what to be. Or, and like I said, I'm going to launch program here. Oh yeah, that today was a day. Here, let me pause this. Sorry, I paused the recording. I just restarted it. So this move bit will move an integer. So right now, this is moving n9:1 into n9:2. We're not executing code because we are offline, so it looks funny. So the way this reads, you would read this is if any bit in B30 is true, because it's greater than greater than 0 would have to be, if any bit were true, execute this move, and this move would be move integer n9:1 into integer n9:2, because we have 255 integers here. So it would be moving this integer 1 into integer 2. These are different values. So we can go, we'll call this 10, 10, and then 20. So you can see that we move 10 into 20. So this could happen. Let's say you've got set points, or you're storing values. One of the biggest examples that happens all the time for data collection would be if an event happens. So if you're trying to track your max and your mins, you could look here and go, if my current value is greater than my last max value, move my current value into my max value. So you can then move integer values around. You can do this with F here. These are floating points. So these will actually allow you to do decimals. You can do that with floating points as well. But it's just move that into the other one, with the caveat that it has to be matching data types for Slick 500s, unless you want to risk losing some data. So if you move like an integer or a float into an integer, it's going to truncate your decimal. Does that make sense? It's like it's not a copy, but it's just this value would then, like, once this executes, 10 would just be go into 20, but n90 would remain 10. Did I answer your question? I'll do the exact same thing in the control logics. I just know more than one of you said you worked with the 500 software, so I kind of want to, if you haven't used 5000 as well, there is a little bit of a learning curve. So I just kind of want to show you like for like, side by side, and how much easier it is to get things going. So you can see here where you have to define, this is like any programming language, you have to define all your variables. So for the Slick, you've got to build out all your data arrays and data tables for all your structures, your integers, your floats, your timers, your counters. They all have to exist, and they all have to be called out before you can use them. Does that make sense? Yeah. So in control logics, and let me say in Slicks, if you need to add to any of these data files, that is a download. So does everybody know what download means? I know I'm kind of running here. So in different programming languages, different hardware, different languages, things are kind of used differently. For Allen Bradley, you have, and I can do this with the emulate mode. So we have here this program right now. You can see that I am online, and you can tell that by seeing that it's in remote run mode. And if I were to come into here, so Whoops. So tag, data type, and description. Access level, so read write. This is a controller tag. So I've now just created and called this tag out while online. Bool 2. I can use those in my program now. Bool 1. Bool 2. No, doesn't like it. Because I can't type. No. Oh, yeah, there it goes. So you can see here, it's executing code. So now I'm online. So when you have a piece of software and you want to go online with a controller, let's go offline. If I have this software, this program, and I want to get online with a controller, I will find it in my communications link, and I have 3 options. I can click go online. If the piece of software I have matches exactly what is on that controller, it's going to go online fine. It'll show up. This graphic will change. We'll see that we're online. The controller's in run mode. Controller's okay. Everyone's happy. If I go offline, and let's say I add a piece of code here. So I go, what did I have down here? Oops. So I'm going to show you this from here quick. So you saw me, I created these tags from my controller tags here before. You can actually create these tags right from the programming window. You just have to be very careful that you create what you want. So we want an integer in the controller scope. So now I've made this edit. It's good. So now if I were to go to this program and I go online, it's going to look at what's on the program and it's going to tell me that there's a different version. So now I have 2 options. I can either upload the code from that controller. Now we all know that what's on the controller is just rung 0. So if you don't know what's on the controller, you almost never want to download, because if you've got a program, if you've got a machine and you just download the code you have without knowing what's online, you're going to overwrite everything. So if I were to upload, it's going to actually erase this edit that I made. But because I know what I want to do, I want to download, and it's going to push this logic onto the controller. So for the purposes of this course, upload is taking the program that's currently running on the PLC and bringing it onto your machine. And download is taking your program from your machine and pushing it to the controller. It's the opposite way that everybody's been taught how to get stuff from the internet. Everybody downloads music from the internet, downloads files to the internet, and uploads to the internet. Alan Bradley decided in the 70s that they're doing it this way. So for Alan Bradley, you download to the program and you upload from the program. I know in some of the other softwares, there's transfer to PLC, transfer from PLC. You just have to be cognizant of what you're doing, because when you write to a PLC, there's no undo. Make sense? Perfect. So here we'll make this, and then here. So we'll do this one online. What was it? GRT.
In this example, N9:0, 1, 2, and 3, is that referring to the byte in that integer, or is that referring to the word?
Both. That's why that's why it's important to know and understand, especially for the older register address-based processors, that the PLC can do them both. So when you look at it here in the greater than or less than, you can actually evaluate based on the decimal value of that integer. But you can also read and write to individual bits of the same integer. So it's important to realize that if you're going to create an integer and use it as an analog value, as a value, to not use the same one to, let's say, put pump run statuses. So let's say you could define N0 through N10 as all the statuses for your pump. So N0 is your in local, in remote running status, fault status of a pump. And then all N10 through N20 could be the speed feedback of the pumps. So you can use integers interchangeably, especially if you're going to use only whole numbers. If you're going to need to use decimal places, so let's say you need to use, you've got a flow meter and something runs at 1.45 liters per second, you'd actually need to define a floating value for here. A floating value, you can't actually get to the bit level information of it. You can only view its whole value.
Over there. Okay.
Does that make
So-
that answer your question? Sounds like you have
Yes.
a follow-up question.
Yes. So like in that case, like when you're doing the move command, moving from source A to source B, you're just moving from one word to the other word, right?
You bet.
Okay.
So no, go
Go ahead.
No,
Okay.
no, you go.
So I just had a follow-up question on that. Like, say, if you're in an industrial setting and you have a lot of data that are being used to confirm statuses and all that kind of stuff, and your limitation on the memory, say, for integer type is 256, but you need additional memory. Is there a way to upsize the memory or add more add-on memory cards or something like that? Or are we limited to 256 in this
So-
case for this particular program?
For the PLC 500s, each integer array. So this n data file is limited to 256, but your total limitation is your 64K for this example of processor. So if you needed to assign more integers, what do I call the other one? Int 2, you could do 256 or well, I typed in 256 and it will not, it'll max it out. But you can have multiple data tables.
Oh, so you can add more. Okay.
Oh yeah, absolutely. So you can, and if you don't want to go to 11, let's say you wanted to go to 100 and make 100 counters and call these counters, and you wanted 100 of those, you can call out these counters, and now you've got counters. Now counters, we'll touch next week, I think, in the coming weeks. They use up more information, so they actually have their own little functions. So you write them and they'll actually increment values, so they hold integers inside of them, so they take up more memory. But you can assign a whole bunch of them. I wonder if I can, sorry. I have a big program and I think I'm going to try to run it for you guys. So earlier I was talking about standards. Do people understand what I mean by like programming standards? I don't mean to be all squirrel and going in multiple different directions. It's how my brain works. So if you need me to finish a thought first before I open up this other program, let me know. Shell that one, will that work? Maybe if I go like this. Perfect, confirmed. You can copy and paste. You can't drag and drop, but you can copy and paste into this RDP session. Let's just do this. 3 and 2, 4. So I'm gonna finish this to kind of show you some of the benefits of control logics. So you saw I'm online right now and I can create these integers, these data types, these tags while I'm as I need them. So 2, 3. That automatically completed that. And 4. So you can see, you saw that turned from red to blue. Red indicated that there was something wrong in that rung. It couldn't compile it. Something wasn't working properly. Once I fixed it, you can see here that we're editing it, but it's valid. Anyone who's worked with the fives and even other programs, you need to accept your pending edits. So here we accept my edits. It's going to kind of check them for valid, but check that they're valid. I obviously can't say that word today. It's going to then put it into operation. So now this code is running. If I had edited a live rung, they'll show side by side. But because this code, you can see here, this green line comes down in front of the rung, it's executing the code. There's just nothing happening here. So if I go make 325 and make this 20, that doesn't do anything. Integer 3 does not move into integer 4. But if I make this 50, integer 3 immediately moves into 4. And if this comes back down below 20, it remains. Now 30, it doesn't change. So does that make sense as to how that executes? And I'm just, this last click here just assembles and makes that edit permanent. If I go back in, if you are online and I double click on this rung, what it's done is it's taken the live rung. This R here is the live running rung. So if these values do change, 50, the code is executing still. And let's say I wanted to add in a, I don't want this to execute if bool 3 is on. I can then push that right through. I did something. Okay, so this last button for the edits, I'm sorry, I skipped that. You know, I was showing you where you accept, test, and then compile your edits. That last button right here does all 3 of those steps in one click. I kind of ruined my own punchline there. Any questions about that? Does the move instruction make sense? Somebody had asked me that earlier. Now that you saw it actually execute in this example, does that make sense to you? Perfect. I'm not going to save that. So when I further on in this program, we do get into templates, programming standards, tagging standards. Excuse me. That term is being used kind of universally. There's some tagging standardized documents that have been created for your labs, for examples, which we're going to follow. If you end up working for municipalities, larger companies, you have, especially if you end up working on tendered drawings, tendered projects, you're going to find that the end users have developed their own tagging standards. So you as a programmer who come in to work in their site, especially if you're a municipality, you could end up with low bidder coming in to work on your system. If you invest in a standard, a tagging standard, everybody must use specific logic to run a pump. Everybody must use specific logic to do X, Y, Z processes. You improve your odds of having consistent code from site to site to site. So this sample S1A is one of the standards that has been implemented at the municipality I work at for our old slick sites. So this is kind of on the way out, but it's an example of one. Since it's old, I can show it to you guys. We've got one for compact our control logics as well, but you can see here that there is all of these data types that have been created. There's tons of background work to be done to allocate this stuff. You've got data tables for analog high limits, low limits, low limits. You got analog EGU mins and max set points. You need to, when you're developing standardized logic, the analog stuff that I'm talking about here is if you want somebody to consistently always do something the same way, you build drivers. So this is an example of an analog driver that would be broken out into a wet well level, a pressure level, where we'll take here this first rung has an alarm enable for a bad signal. If the 4 to 20 milliamp signal is less than or greater than a specific range coming from the card, the signal's bad. there's a timer for that alarm so it doesn't turn on and off too quickly. If the signal comes in and is a little high or a little low, but not so high and so low as to trigger the bad signal alarm, we condition it and force it to 4 milliamps to 20 milliamps. Here, this scale routine will take your analog signal coming in, scale it between 4 and 20, scale it on your analog EGU min, EGU max, and we'll scale it to an actual real world value. So 12 milliamps means nothing to 99% of the people who want to know the level of this well or the pressure of this pump. They're going to want to see it in kilopascals or PSI or something. So it gets scaled in here. So these standards will build. I could, if you're interested, I can send this to you as an example. I don't want to go through every line of code here because you may or may not even care. But when end users develop these, it's so that they get some consistency in what they're doing. So if you always want somebody to evaluate an analyzer in a specific way and have specific high, when I'm talking about high alarms, you'll actually want to know, is the value above a certain threshold or below a certain threshold? And you want to know that for all of these values. You build custom logic for your system, and then you make programmers comply to that. Does that make sense when I talk about standards? All right. And yes, and then here, there is 64K doesn't sound like a lot of memory, especially when we're dealing with like this SLC 500 processor that this standard is built to fit in is, I believe, yeah, 64K of memory. These control logics and compact logics, they have like 200 megabytes. Some of the control logics have, I think, 2 gigs of data of storage. You don't really have to worry about storage on those ones, but these old SLCs, you can run out of memory, but like look at all these data files. There's lots in there as long as you organize it in a logical way and don't waste it. Like if you don't need 255 of something, if you only need 30, only make 30. And this is something that you'll have, if you ever have to size microprocessor data tables or processor data tables, it's an iterative process where you need to know what you need to program before you program it. And then once you program it, you need to go back and reevaluate kind of what you have and kind of shuffle things around. So luckily, the world has moved on from a lot of these processors. You will find them out there. I'm sure the MicroLogicses will be around for a while because Alan Bradley hasn't killed them off, and they are the Logix 500 software, but they're typically for smaller installations. So they're normally for machines, conveyor systems, even just dialer PLCs. When we get back in the compact logics, again, you don't have the same data table. So this controller tags section here, this is your data table. Inside your controller tags, you create everything that you need on a controller scope. So everything, any tag you create here is accessible throughout your whole program. What we've got here is, again, controller tags. You've got a fault handler routine, which we do cover in the other program. This is a routine that runs if your processor faults. We will cover that later. A power up handler, exactly what it says. You can put things, some stuff you can make changes to online, so some stuff you can't. So I'm going to go offline. Inside the power up handler, you can create a routine, and this will only run when the processor boots up. And then once it's done, it never runs again. The fault handler routine is the reverse of that. If there's a fault, it runs and then the processor stops. It's the last thing the processor can do. We can't really test that with the emulator. That's one of the flaws, is you fault the emulator. Well, it doesn't really fault, and the fault handler routine doesn't work. You do need a physical processor for that. And if you have one, by all means, use it. But don't fault a live machine, for the love of God. And if you do, don't say my teacher told me to do that, because I just don't want that on my back. Hopefully somebody laughed. Under the tasks, you've got your main task. So you saw in the Logix 500, you've got one main routine. If you've used those programs before, you have to make calls to all your different ladders. So here you've got your main task. You can create tasks or programs. You got a main task, and then each one of these are different programs. So if you got a main program, you can add in second program. Under main task, you would add a main routine. And you assign it to main. And then under the main routine, this one will always run. If you can see under main task, this one just executes. So again, top to bottom, left to right, the main task program executes the program in this scheduled order. So you can actually rearrange these and run second program before main program. You can run main program first. If you're developing logic on a live system and you want to remove second program, you can remove the second program. It will show up under main tasks, but unscheduled. Now anything inside this program will not execute, even if you're online. You can add new routines. So we can have our routine 1. Type. So routine 1 won't run unless you call it in your main routine. So under main program here, you'll see main. Main routine means what will run regardless of the jump to subroutines. So this main program is the only one that's guaranteed to run unless inside of your main program you add it's called JSR, which stands for jump to subroutine. And you write routine 1. So now when the main program runs and it gets to run 3, it's going to jump to the subroutine. It will complete that subroutine, and then it will come back here. So typically you'll see a lot of well-written code. The main routine is only full of jump to subroutines. Those subroutines then run their logic in whatever order you add them. So if you have 5 of these, you could jump to subroutine 1, 3, 5, 4, 2, whichever order you wanted. You can also add, so this is where the programming languages come in. So you can see here when you add a routine into a program, well, I chose ladder logic, but you could choose sequential function block diagram, FBD. Structured text. Sequential function. Oh. Back in main. That worked. That worked. So you can see as I'm typing here, there's many ways to do a lot of things in programming these PLCs. So when I click on the wrong and just start typing, or if you double click, you'll actually pull up this line. And if you know the short forms for these routines, you can just type them in. So it'll kind of show you the syntax of what you want to do as you're typing it in. So JSR, and then it wants to know the name of the subroutine that you want to show. So I've named it SFC. But here you can also find it in these drop-down lists. So up here, I'll pull this out as far as I can. There are many tabs which are full of different programs, functions that you'd need. And if you know where they live, oh my goodness, JSR, you can find the JSR. And if I click on it, it pops down here. This JSR actually came in expanded. And that's confusing. So, will it accept that? No. Huh. So with some of these routines, especially the jump to subroutine one, here you can actually have parameters assigned to it. I don't want to say forget you saw that, but does anybody know what a parameter is? Indirect addressing. So if you were to jump to a subroutine, and let's say like we had that standard, oh, my speaker turned off. There could be people talking. Oh, you guys must think I'm crazy. Were people talking? No, I'm good. Thank you, Vincent. Oh my God. I have this Bluetooth speaker that just turns off and I don't know what the timer is. I'm going to get new speakers, guys, so that doesn't happen. So with the standardized logic that I was showing you, where everything kind of lines up, everything's done the same way, you can actually set up specific parameter files. So if you had, for example, let's say you have a tag with a special field at the end of it. So does anybody know what like a JSON file is, or like a CSV files? They're standard tag data tables. So you can use that other JSR to kind of fill in the blanks and then return back data. They can be really powerful, but there's a better way to do that, and they teach a different way. I've never actually clicked on this JSR before. I always just type in JSR and it gives the more basic one. Sorry about that. Aside. So here, these jump to subroutines will jump to the different routines so we can watch them execute. Once I download, can I do that? No. So some of these you can't edit online. So in structured text, again, you can type in, that's the last time I've, so you can do tag, spool, one. Why isn't that showing up? I'm not the best at structured text programming. I'm not gonna lie, but you type in here with your different program files, so you can do moves. It's like a notepad. If we were online, and I will go online, I think it will build my syntax for me. I was gonna write some move commands, but I think everybody gets it. Does anybody want to see me suffer through writing lines of structured text? Oh, perfect. SFC, so you can see here your step. You have action evaluation orders. You assign tags to your steps. So if you don't want this to say step 01, you can call this waiting. You assign all your different timers and parameters, how long to wait, when to execute, action orders. You would assign actions offline and you can move them around. So what is it doing? Am I opening? Am I closing? You can call other subroutines. And in your transitions here, you'll set a transition tag. Type in here your value equal to 0. Value would end up being a tag, but you would edit like that. You could see how you remember how I mentioned it kind of shows up on a grid. So it starts roughly in the top left, but it's looking for the first program. It'll run through and you can add new branches, and you just connect the branches one at a time and build your program as you go. Does that make sense? The editing environment for SFC. Function block diagram. Again, you've got your inputs, input reference. You would take a function. So divide. Whoa. So in one. So this is a integer divided by an integer, and then you can output a real value here, but I never created a real value. So again, I can real one. It's a floating point. Read write. Scope is a controller tag. It's created. Invalid syntax. Yeah, the structured text doesn't like my syntax. Great. Because. And this is all gibberish because I didn't add anything. So nothing's happy. but you're fine. Wonderful. Why isn't that running? Oh, I'm not online. Huh. If you're not online, the code won't execute. Another thing to note here, this turquoise color means remote program. You need to see remote run. That'll turn green. Here you can see green means it's executing. That's not happy because that was a 3. That's a bool. What am I doing? 600 divided by 10 is 60. And then that you can see here, 60. So when you're looking at your controller tags, you can see all your values here. You can monitor them. Integers, you've got 600. You can actually see all your individual bits. If you click edit tags, now you can make changes. So we'll go dint 1. We're going to make it a dint. And that tag's created. And you can see dint goes all the way down to 31. So it's got twice as many bits as an integer because it's a double integer. Rockwell always starts at 0. So 0, 1, 2, just like your least significant bit we were going through earlier. You can see your bools. You can delete tags here as well, but you cannot change, well, you're online, but you cannot change your data type. So if you are creating tags online, make sure you create the right tag data type because you can't change it. You would actually have to create a new tag, delete your old tag before you do that. And you can't delete them if something's referencing it. So if I think 3, I can't delete this one because some things are looking at it. And pro tip, it doesn't have to be something inside your PLC program. So in a couple of weeks, when we get to looking at graphical interfaces, if you have a graphical interface, a SCADA system, a touch screen, looking at one of these tags, if it's being pulled by anything, you cannot delete your tag. Okay, any questions? I'm gonna kind of keep going through a tour of some of the features of 5000 we've got going on. So I was talking about main task. We can see here as this one, I said it runs kind of continuously. It will go through, it's going to run the program in order, the scheduled programs. It's going to go main program will complete, and we'll come back to the top. You got some statistics in here, how long it takes to run through the entire program, milliseconds. Looks like something took 92 milliseconds at some point. I was probably doing an online edit. It didn't like, you can reset these stats. Oh, no, some of the stuff took 42 milliseconds. Very fast cycle times on these controllers. So we can add new tasks. You can do some of this stuff online. So there can only be one main task. So if anything you need that needs to run continuously has to go in main task. You can have periodic tasks and event-based tasks. So a periodic task will run, surprise, surprise, periodically. So if you set a periodic task to run every 10 milliseconds, it'll just run every 10 milliseconds. If it takes longer, this one here, this watchdog, if it takes longer than 500 milliseconds to execute, it will fault. The same as the other one, you can add, oh, neat. So there was an unscheduled task. You can move tasks, unscheduled program rather. You can actually move those programs around from main task to a periodic task or to an event-based task if you want, if you have any need to. Periodic tasks are things that you don't necessarily need to run every single scan cycle. So if you have something, if you only need to pull or collect data every couple of minutes, or you want to back up specific registers every few minutes, you can put it into a periodic task and then it will just run and complete that task and then wait. The limits for them, you can see, again, it's in milliseconds, but I think you can go up to like 2 million milliseconds. So you can really drag that out. You can do a couple of hours. Again, this isn't time, it is cycle time based on when you turned on. So if you need something to happen like every 5 minutes on the fives, this isn't going to be what you want to do. But if you just need something to run, again, periodically based on the last time the processor turned on, and then it does have a priority, which means that if the processor starts to kind of lag down, you will shift the priority for the entire cycle. I don't know the last time I actually had to do that with anything in my industry. If you have specific questions about that, I can look them up for you and work with you if you're having a processor watchdog a lot. If you're doing a lot of motion control, you do need to start watching your cycle times for safety, but you're also going to have safety features for motion, especially robots, welding, all of that stuff. I just don't have a lot of current experience with it, and I don't want to speak to something that there could be many firmware upgrades and advancements that I just haven't had time to look into. The last type of task that you've gotten here is event-based, which is exactly what it sounds like. If something happens, then do this. If this, then that. So if you wanted something to happen every minute on the fives, well, you could set up that event. Here, access watch, this stuff is motion. So if something happens with your motion, you need to do something. Not quite safety, but it can, you can do that. If you need to do something based on a specific tag, you can select a tag. And if you populate that tag inside the main controller, if minute equals 5, do something. If timer done, you can do something. Does that make sense? I don't think I have the greatest, I don't think I just gave you the greatest example, but I think it's fairly straightforward. Okay. went a little faster than I thought. So the last thing I wanted to show you guys was a good example of execution order. So if you have, I'll go back to here. So if you need to track every time something turned on, this is something that is done a lot. Is if this were the running status of a pump, and this were the running status of that pump, the last cycle, I built this earlier. And like I said, I lost a bunch of programming and I'm just trying to do this in my head. So if this pump is running, we can see the pump started. This is simulating an actual input from the field, but it's not great. This isn't great programming practice, but for the example, I think this really works. So we turn on the running status of the pump. If the pump is running, but it wasn't running last cycle, count up. So we've counted a start of the pump. And so because this executes last, the running last cycle was off. So if the pump turns off now, it's no longer running this cycle. So if we turn that back on, we only count up once. So we can capture something. If we're trying to do something just once, we can monitor this one status in the last scan. Does this make sense? So then if we move this around, you notice how, because the last scan happens before the evaluation of the running status, it doesn't matter how many times the pump cycles on and off, the order of operations is wrong. So we're not accumulating anymore. So for ladder logic, this really, it's important to know what's going to happen first. I can't tell you how many problems I've come across where the order of operations was just, it was done. It was programmed in such a way that could only work if 1, then 2, then 3, then 4. So if you've got a sequence, so like we were getting into the sequential batch or sequential flow chart, if you have a process that's very, very dependent on if 1, then 2, then 3, then 4, if that's always going to happen and you're never going to have something deviate from it, perfect. But you really, if you have a process that might go 1, then 2, then 1, then 2, then 3, then 1, you really need to pay attention to your order of operation. Does this help? This visualizing and seeing an example of what can happen makes sense for scan order. Does anybody have any questions? Because that's the end of everything I've got for you guys today. So barrage me with questions. There is a quiz for this week, I believe. A couple of questions. Oh, it logged me out. It should be available now. Your 10 of electrical work, still learning more about PLCs and creating more lean programs. From Scott. Sorry, I'm sorry, I'm reading something that you guys can't see. And I'm just trying to confirm that you guys can see the quiz. Yeah. So again, there's a quiz. Due Monday, you should be able to. Can somebody confirm you can see that? My like view as a student isn't working.
I only see the first quiz so far.
Quiz 2 is there at the very bottom. Under week 2, intro to PLC programming.
Fucking speaker. I'm sorry, guys. My speaker is off again. Thank you, Vincent. And my speaker's on now. Okay, thank you, Janessa. So now that my speaker's on, are there any questions? All right. Well, if there aren't any, I'm going to be here till 9 o'clock. Ask me questions. If you want to see something, I can try to show you some more examples of stuff. Again, just a quick tour of the software for the future. I at least like to see something before I get my hands on it. I know some people would rather just dig in with their hands. I'm going to try to get you guys the information on how to get onto these any access computers. There are a bunch of lab notes I went through, our lab tech tips I went through on the weekend. That's how I got set up and found them. Heck, there is some really good, like if you need Photoshop, like these computers are loaded. You need AutoCAD stuff. These things, there's I don't know, $150,000 worth of software on these things. A really cool resource. SolidWorks, Jesus, really cool computers. I might be the nerdiest person here about that. I don't know. I'm gonna try to get you guys access to that. So yeah, I guess class dismissed if you guys want to take off. Have a good week. we'll see you guys next Tuesday. I'll be here for the next half hour trying to figure out how to get that information posted to Econestoga. So thanks, guys.
Thanks. Have a good night.
You too.